So welcome back. So we're going to do standing waves. So what happens, what you notice is if you have a piece of string and you send a wave on it, a pulse, it just travels down the length of the string, you know, as time passes. We've all seen this. And if it hits an end, it will reflect, and it might reflect as a pulse, as a crest, or it might reflect as a trough, depending on what the end is like. That doesn't matter so much. What matters is it reflects. And so when you get like a guitar string, and it's a tight guitar string, and you pluck it, it's like you're sending energy in both directions, and it gets reflected at the ends, and it starts coming back, and it starts interfering. So the energy is like sloshing backwards and forwards, and it's interfering. And it's waves that are interfering. And so what happens is you pick a point, and you're so far from one end and so far from the other end, and what you find is, well, this is my imagination. It's as if it's as if the string is trying to do every frequency of wave possible. And that means it's as if the string is trying to do every wavelength of string possible, because V equals F lambda, and V is fixed for the string. Tension divided by the mass per unit length, yeah, basically, square root of that. So the V is fixed, so the string can mess with the F, which means it's messing with the wavelength. And the rules are, it's got to be a node, no vibration there, and there's got to be no vibration there, but anything else goes in between. So I can imagine, well, that would work, wouldn't it? That would be okay, because I have a node and I have a node, and I can have anti-node in between. But that would also be okay, because the fact that I have a node in the middle, who cares? And that would also be okay. Yeah? So if the string set up frequencies that gave me wavelengths that look like this, they'd be allowed. They'd work. But if the string tried to set up a wave that was that wavelength, where I get a node and I don't get a node there, that can't exist, because it's breaking that rule of a node at each end. So there's a family of wavelengths that match this string, and that causes a family of frequencies that match this string. And all the others fade away. It's not that they, your thumb doesn't know you're supposed to have a 400 hertz pitch to this string. All it knows is put energy in. And it's the string that kind of sorts out what frequencies are allowed, because of its length, because of its velocity of the energy. It self-selects these frequencies. Not just one, there's a family of frequencies. And as we'll find out, there's a very nice mathematical relationship to the allowed frequencies. This could be a tube, it could be a flute, it could be a recorder open at one end and closed at the other. We'll have different patterns of allowed standing waves. Standing wave is a bit of a misnomer. What it means is that when you look at it, it just looks like this little envelope. In time, what happens is that goes like that, which 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 goes like that. If you could do a slow-mo picture of it, you'd see this thing whacking backwards and forwards. But the nodes stay in the same place and the anti-nodes stay in the same place. So you're not aware of any directional motion. It's just all up and down motion. The energy is going backwards and forwards, It's just that because of constructive and destructive interference at different places, those places don't move. So we start off with some math, and again, it's really the visualization I want. So if we have two waves going in opposite directions, so the energy is going in one direction, the energy is going in the other, it's going to hit and it's going to come back. So we're going to get, at any point, we're going to get energy coming from both directions. So one wave is A sine kx minus omega t. Why not have the same amplitude? There's nothing special about the directions. So the A's are going to be the same. In the other one, I have kx minus plus omega t because it's going in the opposite direction. So that's for the opposite directions. We combine these and we get A sine kx minus omega t plus A sine kx plus omega t. And if I remember, I don't know if you remember this, but sine A plus or minus b is equal to sine A cos b plus or minus cos A sine b. And I didn't remember that. Years since I'd used it, so I had to go, oh, what is that again? I can't remember that. And when you put that in, what you find is you get 2a sine kx cosine omega t. And this is a standing wave. Again, you don't need to know that equation. It's just, you know, what do you get out of it? You get out of this pattern where in time, you know, these things oscillate. We'll see this in a lab. But when you look at the envelope is there's always a node, there's always a node, there's always an antinode, there's always an antinode, antinode. It's this fixed pattern. A standing wave is an oscillation pattern with stationary outline. It's the outline that's stationary, that results from the superposition of two identical waves traveling in opposite directions. Now, my advice, the book is full of equations, and they have n's in here, and not in this page, but there's n's kicking around, and man, it's kind of like, my advice is this. This is so that you can, this one here is so that you can show that the exposition of where you get the nodes is you're going to get them at half a wavelength and one wavelength and 1.5 wavelengths. And you're going to get the antinodes at a quarter wavelength or 3/4 wavelength. And all that's saying is, oh yeah, look, there's one there, and there's one there, and there's one there. Oh, and the antinodes are in between, you know. That's really all that's saying. Okay. So I think this is more pertinent, and that is the natural pattern of oscillations are called normal modes. Rule: for a string that is fixed at both ends, there must be a node at each end. So each normal mode has a distinct wavelength. The wave speed is dependent upon things like tension and mass per unit length, V equals square root of T over mu. So for each mode has a distinct frequency, and these are multiples of the lowest frequency and are called harmonics. Yep.
I brought my guitar.
Oh!
If you want, I could bring that in.
Yeah.
And just show you guys real quick the harmonics on the instrument. It's right there.
Can you do it at the end?
Yeah, no problem.
Yeah, good. I'd love to see it, though. It's great. So, what we have is we have allowable normal modes. And I'm showing like the string in one position, but allowable normal modes look like this. I'd like you to be able to draw the first like 3 or so patterns. And then what we do is we say, this is length L in each case. I'm going to say for the first one, I'm going to say L is equal to, and can you tell me how much of a wavelength is this pattern? If you think that's a wavelength. So it's half a wavelength, isn't it? So for this first one, lambda equals, L equals lambda over 2. So let's just find out what lambda is. Lambda equals 2L. Yeah? I just rearranged it. if V equals F lambda, then F is equal to V over lambda, which equals V over 2L. That's for the top one, yeah? Whatever V is, whatever L is, I can work out my frequency. If V is 25 and L is 10, that frequency is 25 over 20. Yeah, whatever numbers you need to put in, yeah? Let's do the second one. For the second one, L is equal to, can you tell me how much of a wavelength this is? It's lambda. I'm going to be a bit cute and say 2 lambda over 2, and you'll see why in a minute. So lambda is equal to 2L over 2. Yeah, I took that to the other side. My frequency is equal to V over lambda, which equals, I'm going to say V 2L over 2. Let's put that 2 on top. Oh, that's 1 times this. And that's 2 times this. Do my third one. That's going to be 3 halves. So lambda is equal to 2L over 3. So F, which equals V over lambda, is equal to 3V over 2L. No matter what V is, and no matter what L is, you can always figure that out. But can you see how it goes 1, 2, 3 for the frequencies? And so we choose to call that the first harmonic, the second harmonic, and the third harmonic. And the harmonics are the ratio of the frequencies. It's not the order of the diagram. So the third harmonics is 3 times the frequency of the first harmonic. The 17th harmonic is 17 times the frequency of the first harmonic. It's not the diagram order, it's the frequency ratio.
What was the percentage for the second harmonic compared to the first?
The percentage?
You said the third was 17 times.
Yeah, if I said, what's the 17th harmonic? It's not on my diagram, it's just the 17th harmonic would be 17 times the frequency. The 19th harmonic is 19 times the frequency. Now here's the thing. So I'd like you to be able to, and they are harmonious. They sound nice together. They're a lot more interested in a tuning fork, because a tuning fork just has the main frequency, whereas these have a family of frequencies. So this is what I want you to know. There are the equations like this, lambda to the n equals 2L over n, and you can see that pattern here. And the frequency of the nth harmonic is equal to V over the wavelength of the nth harmonic, which is NV. And frankly, as my students learn it, man, they fell about all over the place, because the n's are always problematic. And so just work it out. I'm not going to ask you for the 17th harmonic. I'm going to ask you for like one of the first 3 bits, yeah? So just be able to do this. This is the skill. And I will give you a free velocity, and I'll give you a wavelength. I'll say, what's the frequency you're going to hit? I might turn around, having found the fundamental frequency, the first harmonic, I might say, what's the 7th harmonic? You know. From music, some people call this the fundamental, yeah? Fundamental frequency. It's the first harmonic. And then I think these are called overtones, but I'm not sure of the numbering. Do you know the numbering? Is this like the second overtone? I don't know if this is the first overtone or the second overtone or what. I don't know how that numbering goes.
You mean as far as the octave range?
Yeah.
Yeah, I'm not sure. It's not, like the second one's not the next.
Okay.
The third one's not the following.
Okay. It's
I mean,
more
to be honest
complicated.
with you, yeah, if I had to guess, the second one's probably squared.
Okay.
The third one's probably cubed. And when you hear it, you'll hear the significant
Significant change.
octave range
Okay. Yeah. So stick with harmonics, you know. I'll try not to use fundamental, but remember fundamental is first harmonic. You know. So here's an example. A guitar string is fixed at both ends. Well, you knew that. It's 2 meters long. A transverse wave has a speed of 5 meters per second, so we'll just do V equals 5 meters per second. What's the wavelength of the first harmonic? Okay, so we'll just do, well, let's draw the first harmonic. Simplest pattern. I'm going to turn around and say, well, what's the wavelength of it? Well, L is equal to lambda over 2, so lambda is equal to 2L, which gives me that lambda is equal to 2 times 2, sorry, not 5, which equals 4 meters. And then what is the frequency? Well, V is equal to F lambda, so F is equal to V over lambda, which equals V, which we said was 5 over lambda, and we said the lambda was 4, which equals 1.25 hertz. So there's my answer. Now, I could ask you for the second harmonic, I could ask you for the third harmonic. I wouldn't go above that. In each case, I want you to draw the diagram, be able to figure what we just figured out. Okay? I'm going to skip that for a minute. Let's make it more interesting. Let's take so a piano is like a guitar, is like a harp. They're strings fixed at both ends. A saxophone is like a clarinet, is like a recorder. They're closed at one end and open at the other. Yeah. So I mean, I know there's air so you can blow in, but it's largely closed. You're blowing through this little hole. It's just a source of vibration. It's not like it's an open end like the bell of the trumpet, you know. So we got a different kind of instrument now, and I can draw it by. So what are the rules? Well, the rules are you can't have an awful lot of vibration at a closed end because it's closed. So there's going to be a little displacement here and a lot of displacement there. And I suppose I could have little displacement and little displacement with a lot of displacement and a lot of displacement as long as there's a lot of displacement at the end. But I can't have little displacement at the open end and a lot of displacement at the closed end. So it's the same kind of, I'm going to look at rules for this. And the problem is drawing it is a pain. So we cheat. What we say is, this is like a node. It's kind of like a node. There's not much vibration at a node. The string is stuck there. There's not much vibration here, a compression or whatever this is, a lack of displacement. So we'll call that a node. And this is like an anti-node, because the anti-node, things can wobble about all over the place. And there's nothing to stop the wobbling. So what I do is I say, oh, well, the rule for these guys is we need a node at that end and an anti-node at that end. Same down here. Node at that end, anti-node at that end. And then you say, but what about a flute? A flute you blow from the side and it's open at either end. Oh, well, in that case then, the rule for that is there's an anti-node at that end and an anti-node at that end. I'll use the terms an organ pipe that is closed at one end, and I'll call this an organ pipe that's open at both ends. I'm not going to use the instrument just in case you don't get it. So I'm going to use guitar string. I'm going to use an organ pipe closed at one end. I'm going to use an organ pipe open at both ends. But notice this. L is equal to, how much of a wavelength is that? Remember what a wave looks like? Yeah, it's a quarter one, isn't it? So lambda over 4. So lambda is equal to 4L. V is equal to F over lambda, sorry, V equals F lambda, so F is equal to V over lambda, which equals V over 4L. So for that one, that's how I get my frequency. The next pattern is this. If you think about it, I have a quarter wave. I can't use the full wave because it's a compression. It's a node. I have to use the 3/4 wave. So L is equal to 3 lambda over 4. Well, lambda is equal to 4L over 3. So my F is equal to V over 4L times 3. If this is a 1, that's a 3. The frequency of this is 3 times. If this is 100 hertz, this is 300 hertz. What harmonic is that? How do we define the number of the harmonic? What did we say? We said the harmonic is not to do with the diagram order. The harmonic is to do with the ratio of the frequencies. The third harmonic had 3 times the frequency than the first harmonic. So your harmonic number goes with the ratio of the frequencies. So what is this? If this is your first harmonic, what is this? It's going to be your third harmonic, isn't it? Because if that's 100, that's 300. Because that is 1 V over 4L. And this is 3 V over 4L. And there's no 2 V over 4L. That second harmonic does not exist. There is a second pattern. This is the second pattern. But that's not your second harmonic. It's your third harmonic, because the second pattern gives you a frequency which is 3 times your first harmonic. So you got to distinguish between the harmonic is not the order of the diagram that you draw. The harmonic is the order of the ratio of the harmonic, the ratio of the frequencies. By the way, do you want to do me his job? See if you can draw me the fifth harmonic. Can you draw it? Can you figure it out? Have a go. What's it going to look like? What's your fifth harmonic going to look like? I'll show you a cheat after you've had a go at it. Everybody had a go? Here's the cheat. Divide it up into 5 bits. That was the first, second, third, fourth, fifth. But it's like, if this is a fish, this is a double fish, you know. That's a head with a tail. This is 2 heads and a tail, you know. And if you look at it, let's just look back. So let's see if that goes. So that's 1 bit, isn't it? That little envelope. So your first harmonic looks like that. Your second harmonic looks like 2 of them, but it's squished into the same space. And your third harmonic looks like 3 of them squished into the same space. And for the next one, your first harmonic looked like that. So your second harmonic looks like that So there's no second harmonic, but your third harmonic looks like three of them, you know, that, and that. And your fifth harmonic looks like that, that, and that. There's no second harmonic, there's no fourth harmonic. And I can even show you for this guy here. Look at that. That's what you got, and there's two of them, and there's three of them. So you get the base pattern, and you finagle it, you know. For this, can you see how for this organ pipe that's open at both ends, it's just the inverse pattern. If the guitar string was like that, this one is just the opposite to it. You do that, and you do that. But it's anti-node with a node in the middle. So this is a node with an anti-node and a node. So they're just opposites of each other. So again, we have a first, we have a second, we have a third. The skill is I'm going to give you one of those pipes or a guitar string. I'm going to say, draw me the pattern for the second harmonic of the guitar string. I'm going to say, what's the frequency, given this other information? I might turn around and say, what's the frequency of the seventh harmonic? So that's the skill, yeah? Catch-all question would be, a little catch question was, does a organ pipe open at one end or closed at the other have a fifth harmonic? Yes, it does. Does it have an eighth harmonic? No, it doesn't. Does a guitar string have a 10th harmonic? Yes, it does. It has all the harmonics. So there's that bit about what's allowed and what's not allowed. Can you mark on your nodes and your anti-nodes? Could you go node, anti-node, node, anti-node? It's that kind of skill. Okay? Organ pipe is open at both ends. It's 5 meters long. Speed is 330 meters per second. That's the speed of sound in air. What is the wavelength of the second harmonic? Second harmonic, 2 bits. Oh, L is equal to lambda. Yeah, L is equal to lambda. So lambda is equal to L. So lambda is equal to 5 meters. That was pretty straightforward. What's the frequency? V is equal to F lambda, so F is equal to V over lambda, which equals V, 330, over lambda, which is 5, which equals 660, I think. 66 times 10 will be 660 divided by 2. Yeah, 66 hertz. So it's that is basically the skill. You know, remember that's an anti-node, that's a node, that's an anti-node, that's a node, that's an anti-node, and you know, you're off. If I asked you for, now be careful with this, if I asked you for the third harmonic, what would you put down? Can you have a go at that? Can you just write it down? The second harmonic is 66. What's the third harmonic? What would that be? A common mistake is people will put down 180, 196. Because they're forgetting that that's the second harmonic. So you've got to divide that by 2 to get the first harmonic, and then multiply by 3. So it would be 99 hertz for the third harmonic. So watch out for that. You know. Cool? Open on one end and closed at the other. Six meters long. V equals 300 meters per second. What's the wavelength of the third harmonic? There's no first? Oh, okay. Third harmonic. There's my first pattern, and then I reverse it, and then unfortunately, you can't just give me that and that and that, because that's not realistic, you know. So you got to remember that this guy reverses. L is equal to 3 lambda over 4. It's 3/4 of a wavelength. There's 1/4, there's 2/4, there's 3/4. Yeah? So lambda is equal to 4 over 3L, which equals 4 over 3 times 6, which equals 8 meters. V equals F lambda. F is equal to V over lambda, which equals 300 over 8, which equals 3 8s are 24, carry 6, 5 8s are 40, 6 8s are 48, 7 8s are 56. Watch out, it was the third harmonic. I'm not above asking you for the third harmonic wavelength and then the fifth harmonic's frequency. You've got to do that extra bit where you divide by 3 and then multiply by 5, yeah? Can an organ pipe that is open at both ends have a second harmonic? Yes. Yeah, you bet it's like a guitar string. It's the organ pipe that's open at one end and closed at the other. Can't have the even harmonics. I want to go back and look at one. So this is basically just saying that if a period, so what's going on with the musical instrument? Well, you're putting energy in and you're letting it vibrate around. But that's because the guitar string is closed at one end. It's closed at both ends. The energy is kind of trapped. But the other ones, the energy is not trapped, is it? With a flute, the energy can come flying out of the ends, and it does. So what's going on with those is that you continue to provide energy. And you blow continuously. When you stop blowing, you stop getting the sound. When you continue blowing, you continue getting the sound. And if you played a brass instrument, I suppose what am I doing here? Yeah. When you play a brass instrument, you kind of talk to, but that's not what you hear. You don't hear. You hear the saxophone, or you hear the trombone or something. When you play the flute, I don't know how you play the flute. You blow over a reed, and that causes the vibrations. But it's not the vibrating at the note that you hear. You're just causing a source of energy with that vibration, and then somehow your fingers and the tube are sorting out what you hear. What's going on is kind of interesting. Imagine that the is producing all possible frequencies, and it doesn't sound like it, but just assume it is. All possible frequencies. And then most of those frequencies are completely inappropriate for the length of the tube, and so they don't obey the node at one end, antinode at the other, or in the flute, the antinode and the antinode. They don't fit. They give the wrong wavelength, so they die out. And of those that are the right frequency, then what happens is they cause resonance. And resonance is what we did with the resonance tube. The driving frequency. Oh, who's in my lab? Are you all in my lab? Did you all do that lab already? Yeah, I've only got one lab, so that's, yeah. So the driving frequency. So when I went, and the thing, ooh, as the liquid fell, all frequencies, it's picking out the ones that match the length of the tube, and it's amplifying those. And that's what an instrument does. As you change your fingering, you're changing the length of the tube, so you're changing the note that you're interested in. So that's what's going on with that. Good. And it actually is technologically very important because it can cause, if you have a driving frequency like a howling wind that matches the resonant frequency of your bridge, you can destroy your bridge. And there's a Tacoma Narrows Bridge fell down 3 months after it was built because the wind was just the right speed, and that was just bad luck. You know, it ended somebody's career. And radio sets work by tuning the natural frequency of the radio to the driving frequency of the radio station. And because they're matched, you hear that radio station. That radio station over there, wrong frequency, I don't hear it. I still collect it, it comes into my radio, but I don't amplify it.
Why is it that they're always in odd numbers, the radio frequencies?
I don't know. I think that's just they laid them out that way. There's nothing special about that.
My dad's electrical engineer, and he's worked with radios before. He told me there's a reason behind it.
Is that right? I don't know. I honestly don't know why that is. Okay, yeah. Find out. Because I don't know. Almost there. We're going to do beats. This is again, you have two waves superimposed on one another. The difference is they're not the same frequency. So it's like one speaker is giving me 60 hertz and the other speaker is giving me 62 hertz. What do I hear? I actually hear the average. I hear the average of the two frequencies. I hear 61 hertz in that case. But superimposed on that hum, there will be a modulation of the loudness. I won't just hear a hum, I'll hear a hum, and that's because I'm getting beats. I can show you a visual analog. Here's a pattern of darkness and lightness, and here's another pattern of darkness and lightness, and they look similar, but they're not exactly identical. But when I superimpose them, you can see how you get these clearly different patterns where, because of the difference in the frequencies, you get this hum, hum, hum. In sound, there'd be a sound wave, and it would have these like envelopes, a bit like standing waves, but this is in time now, not in position on the wave. Math. There's one wave. There's another wave. Slightly, and so I'm sorry. Omega 1 and omega 2. I chose to put 2 pi f1 and 2 pi f2 instead of the omegas. I don't know why I did that. Cosine A plus cosine B equals 2 cosine A minus B over 2 cosine A plus B over 2. So I substitute that in there. And the answer is that the carrying frequency, the hum you hear, is the average between the two frequencies. And the wow, wow, wow that you hear has a frequency which is the difference between the two frequencies. And if I get out of here, go to discard, go to here, go to PHET, go to, don't want video though, PHET, oh, I want to be there. Sorry, thanks, yeah. PHET, I go here, I go physics, I go, come on, sound and all that kind of stuff. I hope it's here. Do you have it? Actually, this is. I'm just going to stop for a minute. Actually, I'm not going to. I'm sorry. I shouldn't do this. I'm changing horses in midstream. So here's the. Let's do that. You're just giving me, let's just get one of these out. Discard, discard, keep. I don't really want to download it. Oh, you're not loading Java, are you? Is that what I just did?
Yeah, I'm pretty sure that's.
Well, it probably requires JavaScript in order to show the.
Yeah, but I think I had an old one. I think I had an old copy of JavaScript on it. Run it. Okay, yeah. Okay, so is so listen to a single source, and are you giving me sound? Speaker. Can you hear it? Can you hear that? No, probably not. Audio enabled. I'm still not hearing sound. Oh, that's because I'm down here. Close your ears. Yeah. Okay. So here's the sound. And I can change the frequency. Or the amplitude. Oh, it's killing my speakers. Now. Oh. Two sources. Let's do frequency. Well, let's not do too much. Now, what I can do is, I can pretend I'm I'm right in between. I'm in that destructive interference, constructive interference, destructive interference, constructive interference. So this is a good thing to play with, okay? Let me get out of here. Let me go back and just see if they have beats. I'm amazed that they don't. I'll probably get, what, Dr. Dre on here or something? Yeah, beats.
Actually, just type in Dr. Dre.
Yeah. Beats physics demo. Videos. Yeah, this will do nicely. So identical tuning forks, a little mass thing so you can change the frequency. That's interesting. It's going to put them face to face, so the driving frequency of one will match the natural frequency of the other. Okay, so there's that guy. That's vibrating. He never touched it, but because it was the same frequency as the driving frequency, it absorbed energy and started vibrating. Now he's going to change the natural frequency of one of them by just adding a bit more mass. Different notes. Now the driving frequency is not the same as the natural frequency. Nothing. The same amount of waves came in. It said, you're not my natural frequency, I'm going to ignore you. Now watch this. There's one. That's the beat frequency. And if he adjusts where that height is, he can control the beat frequency. He didn't, of course, but that's what beats is, okay? So the math is simple. All you have to do, I'm going to stop you before I get somebody going on about something wacky. Escape.
I'm gonna watch it.
Yeah. And I don't need you, and I don't need you. Okay. So I'll come back down to here from current screen. So I come down to here, and I say, what's a pure tone of what would the beat frequency be? Need to come down here. So I'd say my F beat equals F1 minus F2, the absolute value, which is 1260 minus 1258, which equals 2 hertz. It's never a negative number. You just get the absolute value. Then what's the carrier frequency? F carrier is equal to the average, 1260 plus 1258 over 2, which equals 1259 hertz. There's my 2 of that. Sound quality. How can I tell whether I'm listening to a guitar or a piano using a little radio? I mean, they're both playing the same note. They're both playing 512, and yet you don't get confused. You'll go, oh, I wonder which one that is. They've both got the same harmonics, both got the same fundamental, same first harmonic. And yet there's a quality difference. We can tell, no, that's a saxophone. Not saxophone. No, that's a harp. Or no, that's a guitar. Or no, that's a piano. They're playing the same notes. And what it is that it's the ratio of the magnitudes of the harmonics. This is just made up. I mean, these examples are made up, it's like. But yeah, they've all got 100, they've both got 200, they've both got 300, they've both got 400, but this has a bigger 100 than a 200 than a 300, and this has a bigger 200 than a 100 and a 300. So they're playing the same family of frequencies, but with different patterns to the amplitudes of them. And so they sound distinct. And our ear, our aural system is just our aural system is just so good that we can distinguish between them. We can have a little recording of somebody on a piano pressing middle C and somebody on a guitar plucking middle C, and we can go, yeah, piano and guitar. We can have 5 instruments playing the same, and we would be able to say there's a saxophone, there's a banjo, we can distinguish between them, and that's coming out of one speaker. That's not because we have stereo speakers or 5 speakers. That's one speaker. We can distinguish. Imagine trying to do the same with colors. You put lights, 3 different hues, 3 different colors of light. It goes towards white light. You do pigments, it goes towards brown. It gets murky, it gets messy, it gets muddy. And yet, for some reason, our ears are able to hear. It's only one piece of wire with electrons going backwards and forwards. It's all one signal in the end. And yet, from that one signal, we can pull out of that. That's a piano. And there's also a guitar on there. And we don't merge the two and say it's a pig guitar, you know. We kind of know there's 2 instruments. We don't get them confused. You can't do that with pigments. You can't mix pigments and get, oh yeah, that is red and green. Or red and yellow. You can't say that's red and yellow. It just looks orange, I think. You know. So it's a weird kind of system. That's all out. So no timbre and know how it works. So do you have time?
I'm right out there.
So he's going to go and get his guitar and he's going to show us some of this stuff. This is really exciting, actually. I'm really pleased.